Hello there! Welcome to Group 20 video, which will be presented by me, Janavi Kurin, and my partner, Tiong Yi Lian. We will show the solution of using numerical method for problems relating to partial differential equation. Before we move on into the problem solving, allow me to explain a little bit on partial differential equation, or just PDE for short. Okay, so PDE is the differential equation with two or more independent variables. Notice that the differential equation showing on the slide is a PDE of second order because let's say the capital T represent temperature. We can see that the temperature is with respect to time as well as with respect to the variable x. Hence, T, the capital T temperature is a function of two terms. That is T equals to Fxt. X and T are the independent variables. There are two independent variables, so it is a PDE, and it is a PDE of second order since the highest degree is 2. There are a few numerical methods to solve PDE problem, and one of them is finite difference method. Particularly, finite difference method is used to solve elliptic PDE. The example of elliptic PDE is Laplace equation, which we will encounter later. So now I will briefly show the derivation of the method's formula. Consider a rectangular region with function uxy as the boundaries. Then suppose that the region is divided into a network of square mesh of side hedge as shown on the slide. Now look at the point uij on the mesh. By moving forward for hedge distance in x direction, we obtain another point called ui plus 1j. And then by moving backward for hedge distance in x direction as well, we obtain another point ui minus 1j. And we can find the difference between uij with ui minus 1j and also the difference between uij with ui plus 1j. Hence, for the independent variable x, the forward difference and the backward difference are described as shown in the slide, whereas the central difference is the combination of forward difference and backward difference. It is similar for y direction. When the point uij move forward for k distance in y direction, the point uij plus 1 is obtained, and when the point uij move backward for k distance in y direction as well, uij minus 1 is obtained. Then we can also find the difference between uij with uij plus 1 and also the difference between uij with uij minus 1. Hence, for the independent variable y, the forward difference and the backward difference are described as shown in the slide, whereas the central difference is the combination of forward difference and the backward difference. Next, if we consider both forward difference and backward difference all together for the x direction, it implies the second order PDE for the independent variable x, which have the formula of forward difference plus backward difference over hedge. And similarly for the y direction, if we consider both forward difference and backward difference altogether in y direction, it implies the second order PDE for the independent variable y, which has the formula of forward difference plus backward difference over k. Now I will briefly show how to solve an elliptic PDE, the Laplace equation for instance. The Laplace equation is given d square u over dx square plus d square u over dy square equals to 0. Notice that d square u over dx square has been formulated in the previous slide. Similarly, d square u over dy square also has been formulated in the previous slide. So we just substitute what has been formulated, and after substituting, the second line is obtained. Then, suppose that the distance h is equals to the distance k, then the fourth line is obtained. And in order to find the point uij, in order to solve for the point uij, we can rearrange and obtain the formula as shown on the last line. Here is the visualization of the formula. The solution at each point uij in the grid or mesh is depending on the solution at neighboring 4 points. The neighboring 4 points are ui minus 1j, ui plus 1j, ui j plus 1, ui j minus 1. And this is also called a 5-point formula, since by the visualization we can see it as a 5-point molecule.
So after listening to the explanation on finite difference method, we will be applying the finite difference method to solve partial differential equation problems in the past year question. So this is the past year question we will be looking at. This is a past year question from the final examination of academic session 2018/2019. We start off by considering the following boundary value problem. It contains two initial conditions and two boundary conditions, with x being less than 1 but more than 0, and y being less than 2 but more than 0. We need to solve the linear system by using finite difference method with central differencing approximation. Note that it is given that delta x is 1 over 3 and delta y is 0.5. The question requires us to perform two iterations using the Jacobi method in order to solve the system. So now I will be explaining the solution to the past year question. Since the question has asked us to solve using finite difference method with central differencing approximation, we will first derive equation 1 and equation 2 from the central difference formula. Then, we substitute equation 1 and 2 into the Laplace equation given by the question. After obtaining the equation above, we substitute delta x equals to 1 over 3 and delta y equals to 0.5 into the equation to get the equation below. After further simplifying, we will obtain a formula which is 9ui plus 1j minus 26uij plus 9ui minus 1j plus 4uij plus 1 plus 4uij minus 1 equals 0. Note that the initial conditions and boundary conditions can be represented as the figure shown on the left-hand side. We note that there are a total of 6 nodes. We will be forming equations at each node using the formula obtained. For node 1, we obtain the equation 9u21 plus 4u12 minus 26u11 equals to negative 97 over 36. Note that U03 and U10 is substituted with initial conditions. The same will be done for others which are not node 11, 12, 13, 21, 22, and 23. And for node 12, we have 9U22 plus 4U13 plus 4U11 minus 26U12 equals to -9. So these are the equations for node 13 and 21. And these are the equations for node 22 and 23. After we have obtained all the equations at each node, we will rearrange them as follows before performing the Jacobi iterations to solve for U11, U12, U13, U21, U22, and U23. For the Jacobi iteration method, we will choose all the initial guess as 0, and we will obtain the value for the first iteration for U11, U12, U13, U21, U22, and U23. We will continue with the second iteration by choosing U11, U12, U13, U21, U22, and U23 as the value we have obtained in the first iterations. Since the question only requires us to do 2 iterations, therefore the system is solved and we have obtained U11 equals to 0.1066, U12 equals to 0.5189, U13 equals to 0.9772, U21 equals to 0.1561, U22 equals to 0.13099, and U23 equals to 0.3692. Now I will be presenting the real-life problem of a partial differential equation which will be solved using finite difference method. Here we have a question which describes a real-life problem of a partial differential equation. Hydrostatic pressure can be expressed as hydraulic head, defined as the equivalent height U of a column of water exerting that pressure. In an underground reservoir, steady-state groundwater flow satisfies the Laplace equation. Assume that the reservoir has dimension 2 km times 1 km and water table heights are presented as follows. We need to compute U11, the head at the center of the reservoir. We will try to solve the problem using finite difference method. Same techniques are applied here as we did in the past year questions. For this question, we have 4 nodes, and we assume delta x and delta y to be 0.1. We will obtain the formula, which is ui plus 1j minus 4uij plus ui minus 1j plus uij plus 1 plus uij minus 1. We will form equations for the 4 nodes using this formula. So these are the equations for node 11 and node 12. And these are the equations for node 21 and node 22. The equations will be rearranged as follows before performing the Gauss Seidel to solve for U11, U12, U21, and U22. For the Gauss Seidel method, we choose initial guess to be 0. Then we will obtain U11 equals to 0.005, U12 equals to 0.006385, U21 equals to 0.006474, U22 equals to 0.008575. After that, we will compute the second iterations. Therefore, the system is solved and we will obtain the values for U11, U12, U21, and U22 as follows. That is all for our animation video. Thank you for listening.